Yes. All right. So the next 10 minutes, I'm going to talk about the Universal Library. It's an effort to build a collection of number systems that will allow us to do some research in multi-precision algorithmic research. So we are looking for number systems and tailor them to the application. That's really the goal. So what is, how do I move forward? There we go. There we go. The Universal Library is a C++ header only, featuring plug-in replacement for native arithmetic types. Right now, we have a broad range of number systems, and they're all sort of tailored to study efficiency improvements for more complex algorithms. We have integers, decimals, fixed points, rationals. Then we, of course, have the linear and tapered floating points and logarithmics. And this day, I've learned of a handful more, so it would be quite nice to add these when we get time or when people are interested in contributing. As I said, the whole purpose for the library was to start building a collective knowledge base for tailoring number systems to applications. And in that process, we sort of discovered that when you don't know an application, you really would like to have a number system that is multi-precision and adaptive. So we have some adaptive multi-precision pieces that we then use for characterization. But then the next step is when you know your characteristics of your algorithm, you can then go into a configuration, an arbitrary configuration, fixed point or floating point or posit, and make progress on potentially a hardware study or a power estimate. Why, taking a step back, why are we sort of interested in this? Well, one of the observations that you have in the universe of embedded intelligence is that we see this rapid proliferation of hardware environments. And another sort of important aspect of this is the hardware environments tend to be very concurrent. So the development of new algorithms and to deliver intelligence to these embedded devices, it would be nice if these algorithms represent or produce the same results across all these different form factors and concurrency mechanisms. And that's one of the reasons that we got interested in building this tool set so that we can, one, get information about the difficulties there, and then hopefully research and develop some answers to these to overcome these problems. So the vision of Stillwater is really to build that high productivity runtime for these embedded intelligence applications, and then the Stillwater company will optimize the performance for these underlying platforms so that customers can basically use that platform and move to whatever their SKUs demand without penalty. So if you then look at the characteristics of these embedded intelligence, it's the number systems that really drive innovation there. So the first observation is pretty obvious, is that most constraint solvers are memory bound. So any efficiency improvement in information encodings will have commercial value. This is clearly borne out by all of the big incumbents that are active in the AI deep learning space. All of them have pitched IEEE floating point, and they've replaced it with something that is much more energy efficient, much more resource efficient, so that they can build services that are 100x faster, 100x more capable than their competitors. But in deep learning is not the only application. There is still model predictive control, any type of simulation mechanisms. So there's still many improvements that can be pursued. These pertain everything from discretizations and curve fittings to transformations and adaptions. The one that I'll focus on a little bit today is the numerical stability within different concurrency environments, and that's where the posit angle comes in for those that are keeping score. So we are part of the steering committee for the posit architecture. And the reason that we started looking at it was this problem of reproducibility when you have a parallel processor that is thousands of cores. The the fact that that posits sort of articulate a solution to user-defined rounding, or having an answer to rounding error. That was what got us involved with the posit arithmetic standard, and we started Universal actually as a posit hardware verification library. But once we sort of got more in the marketplace and asked people what their pain points were, they were all asking for a much broader range of number systems. So that's when we started with integers and fixed points and rationals. So just so that this presentation can also be seen independently of the other talks, just a quick introduction to posits. Posits are a tapered floating point system that is parameterized in two variables. One is the size of the posit, and the other one is the size and the number of exponent bits. That parameter defines a scaling factor, and that is what tapers the encoding of the reals, what gives posits this really rich dynamic range for small sizes. The other aspect of the posit standard is the superaccumulator. So the quire is an entity that allows you to accumulate unrounded results. And these results can come from additions and multiplies, and now give you an opportunity to do a non-trivial computation without incurring any rounding. The only rounding that happens is when you, as a programmer, make an assignment back into the posit that you set. And the example that is given here is a typical fuse dot product that is implemented in the universal library. And you can see that sort of the quire is programmable visible. It is tied to the posits that it's accumulating. And the reason for that is that the size of that quire is very dependent on the dynamic range of that posit. So they're sort of tight, and then they become available to the programmer to direct that computation that they would like to have more fine-grained control over the rounding error. And then the last piece in the context of developing algorithms and characterizations of perfectly tailored number systems for algorithms, the valid encoding takes some of the old unum characteristics, which is the U bit, and adds to that an upper range and a lower range interval type arithmetic to it. And the valid encoding is really useful for doing these characterization type studies where you're trying to discover what the numerical properties are of the execution that you're observing. As said, the Universal Library is an open source library. You can pick it up here at github.com Stillwater SC Universal. We have roughly about a dozen contributors, and we are always looking for folks that are willing to either implement their number system of choice or are interested in contributing examples of numerical properties or numerical problems that need to be solved by a tailored number system. We started Universal about 3 years ago, 2017. It has been integrated in production quality code in about the past 2 years. It has platform support for anything from Linux to Arduino, and pretty much supports all the compilers that we can get our hands on. On the left-hand side, I give you a quick overview of how the library is organized. The two major segments, of course, to call out are the areas where the number systems are managed. You can see that in the sort of the middle of your screen. And there you have your decimals, your fixed points, your floating points, your integers, and your logarithmic entities. And then there is an example section where we basically take computational science and computational engineering applications, boil them down to sort of the essence of either the algorithm that is the bottleneck or the algorithm that is the performance, power, or accuracy problem. And we are boiling them down there and present them as examples where people can play with it and get examples and ideas of what can be done next. And it's sort of important, sort of the basic tenet of the universal library is to create the separation between the driver in which you set up the selection of your number system and the kernel that will be parameterized in the numbers that the number systems that you would like to select. So here's a very simple example. There's a driver that that selects a posit and then articulates a real number system that has that property, that has the posits properties, will create variables and then calls these kernels that are parameterized in these number systems. So another more complicated example would be a conjugate gradient, where you have a residual calculation that would need high precision, and you would have a linear algebra sparse matrix vector operator that could be done in lower precision. So there, the parameterization would happen in 2 parameters. And that's the basic essence of how we sort of build universal. There's a driver that sets up your number system selection, and then there is a parameterized kernel that can take these different number systems and produce the arithmetic that you're interested in. Of the past year, as indicated, we Stillwater are mostly interested on building now on top of that, particularly taking advantage of the quire and creating these what we call high performance reproducible libraries. And the past year, we've built a runtime that is a matrix tensor library. That actually hides all this nuance between selecting a linear algebra operator that has a fused dot product operator. So for example, if you give it a Krylov solver, or if you give a Krylov solver in this MTL a posit value, it will actually use fused dot products in the Krylov solver. And if you give it an IEEE, it will use a non-fused dot product operator. And then on top of that, we are basically building these hyper libraries specifically for the application spaces that they're specialized for. So we have a BLAS, we have a DSP, we're working on a control and a deep learning mechanism. And then the last piece that is sort of going to see some activity this the second half of this year is tensor compositions. Then to summarize and to sort of give you an example of the type of things that we've been doing with the Universal Library, here's an empirical study of a chaotic system, in this particular case, a Lorentz ODE. And what we've tried to do here is try to figure out what size posit would be creating the same trajectory of that chaotic system that, say, the golden reference would do. So we've take the golden reference as a 64-bit posit there in the bottom row of this value of the screen. And then we run simple empirical studies where we're basically looking at the trajectory that the ODE solver goes through as you give it different posits, right? And there you can see that sort of the 16-bit, 18-bit posit would be a place where if you would build a piece of custom hardware, you would like to put some more energy on trying to understand what really the cutoff is where you would lose accuracy or build the wrong predictions. So in summary, we are finding ourselves in this really rapidly changing environment where systems are getting computes embedded in them to imbue these systems with intelligence. These products really need performance and flexibility. And because these are spread out over SKUs that have very variable degrees of concurrency, reproducibility in that context of multiple SKUs of concurrency is very important for the productivity of building these algorithms. And the Universal Library is sort of presented here as the means with which you can accelerate your own algorithmic research so that you can maximize performance or power efficiency for the algorithms that you may be interested in. So with that, any questions?